shared with you. So we are going to start the last topic, which is turbo machinery. So because it is quite wide topic, so we are going to discuss it, the basics, and as well as some application of turbo machinery in the coming weeks. So before we do that, we need to start from the basics. So because in turbo machinery, because we know that there is a stator part and then there is a rotor part, right? So stator part is on which the rotor blades are attached. So when there is a rotation involved in the fluid, so it means that we are talking about the angular momentum, right? Angular momentum and what else? Torque, right? So the applications of turbo machinery involve two types of machines. One is pumps where the energy is given to the fluid, right? So energy is given to the rotor so that it can increase the pressure of the fluid. And the second part is turbine, where we extract the energy from the fluid uh, with the help of rotating blades, and then that energy is being converted into electrical energy by the use of generators. So that is another application. So, but we are going to discuss these two applications in more detail in the coming lecture. Before doing that, we are going to start from the basics. So in order to cover the basics, as I discussed about that, we are going to discuss angular momentum, then moment of momentum equation, and then net torque on a system and things like that. So for that, I have chosen this book of Angel, Angel, and I think Kimbala. So I have also given you the textbook, and we are starting from the section. Let me see. Section is 6.3 from that book. Section 6.3. Right. So first of all, so please keep in mind that for this turbo machinery, for this revision, we are following this second textbook, which is Hindal and Kambala. I have already given you the PDF of that. So in this, we would discuss the basics of rotation and things like that. So hopefully, most of the things we have covered. So if we talk about first of all, if we talk about motion of a rigid body or rigid body motion, it has got two types of motion. First is translation, and then the next one is rotation. And both motions occur at its center of mass, right? So translation motion has been covered already in chapter number 5. If you remember in FM1 that we talk about the translation motion. So it was covered in chapter number 5 when we applied Reynolds transport theorem. To derive linear momentum equation. Right. So just to refresh your memory, if you remember that the Reynolds transport theorem was dB system by dt. So here d is the total derivative or substantial derivative we call it, and then that is equal to partial by partial t integral upon cv and rho b into dv. Here dv is the volume with this with straight line here, and then the the flux going through the control surface. So that was rho v into v dot n into dA. D is the control surface area. Now, this capital V is extensive property, which depend upon the mass and volume of the system. This V is the intensive property, which does not depend upon the mass or volume of the system. So For the momentum equation, if you remember that B was equal to m into V, right? So correspondingly, small b was equal to V. V is the velocity, right? So for the linear multiplication, we know that this left-hand side becomes rate of change of momentum, linear momentum, and we know from the second law of Newton's second law of motion that rate of change of momentum is equal to net force on the system. So we can just write here F net on the system, or CV. If control volume is coincident with the system, we can write F net on the control volume, and that would be equal to partial by partial T rho into volume velocity into dV, which is here, which is the fraction of volume, and then we have got the second term of that momentum influx and outflux. So we call it we call it basically the flux term. N into dA, and A is the N is the inner normal outward from the surface. So this was something you must have studied in FM1. Now we are going to talk about the angular, because now for the turbo machinery, because there is rotation, so we need to talk about the moment of momentum equation. So that is what we are going to discuss. But before we discuss that moment of momentum equation, we need to discuss some basic parameters involved in the rotation. So let me show you a diagram here, and then we can start the discussion from here. So, okay, so first of all, if we want to know the amount of rotation of a point in a rigid body, so that can be expressed in terms of angular motion, which is theta in this case, right? Theta tells us the amount of rotation, right? And then it is basically the angular distance which is swept by a line of length r in a which is normal to the axis. So we know that, and then we also know from our basic knowledge that omega is v upon r, or we can say v is equal to r omega, right? So v is the tangential motion, and omega is the angular velocity here. This is angular velocity, and v is the tangential velocity, which is shown here. Tangential velocity of the point at a radius r. So I hope that these things are clear to you from your basic knowledge of statics and dynamics. So we are just revising it. So then we also know that theta is expressed. Sorry, theta is usually expressed in terms of radians, right? And we know that in a circumference of a circle there are 2 pi radians, right? So we can say we can relate degrees with radian by 2 pi radian is equal to 360 degrees, which is the total theta covered in a longer circumference. So from here radian can be 360 divided by 2 pi, which is 57.3 degrees, right? So I hope that these concepts are clear to you. I am just quickly revising them because we are going to use all these things in thermomachinery application when we are going to start that, right? So it was it, and now we talk about the angular velocity. So we know that angular velocity, that is given by omega, and that is rate of change of that angle theta, which is the angular distance covered in per unit time, right? So if we want to know d theta upon dt. So first of all, we need to know that uh, how much angular distance it has covered. So if I say that if you remember that there was a relation between arc s is equal to r theta, that relation. So s is the you can say that could be linear distance covered. So I would say that this is the arc length. And so in the book they have taken it. If we talk about that could be linear distance, so they have taken it equal to length, which would be something like here. This distance is L. So L is equal to r theta. From here we can say that theta is equal to L upon r. L upon r. So L is the that linear distance covered, which is angular distance covered. We can say it. So from here we can put the value of theta, which would be d L upon r upon dt. So now because r is the same for the rigid body, so we can say that omega is equal to 1 upon r dl upon dt. Right? So dl upon dt from this figure, that would be 1 upon r into v. V is the tangential velocity at that point. So from here we can say that omega is equal to v upon r, which is the case because we know that v is equal to r omega. Right? And similarly, there is another thing which we, because velocity has one thing which is magnitude, and then there is another thing which is direction. So because in the circular motion, the direction of velocity is always changing, so there would be some acceleration as well, angular acceleration. So we call it angular acceleration. And in the book, they have defined it with alpha. So alpha is the rate of change of angular velocity. So then again, if we kind of try to find its relation, alpha would be equal to d omega by dt. And then here we can just put the values of omega. Omega is v upon r. So d upon dt, dt, v upon r. Then again, because the radius is not depending upon time, it would come out of this differentiation and 1 upon r dv upon dt. And then that would be equal to 1 upon r at. T means tangential acceleration. Right? So we can say that at is equal to r alpha, and alpha is the angular acceleration. Right? So these are the two relations which we need to know, both angular acceleration and the angular velocity, which I hope that we already know from our basic knowledge. So I hope that there is no difficulty here. So, but again, if you have got any point which is not clear to you, you can ask me anytime during the lecture, just to make sure that you understand the concept, because the upcoming concepts would be based on the same knowledge which we are covering now. So now, if we want to know that what is the force which is going to act due to this angular acceleration. So because for the linear case, for the linear motion, we know that the relation is F is equal to ma, right? Which is the mass into acceleration in the linear acceleration. But now, because we are talking about rotation, so it means that we would be talking about something which is related with the rotation. So it means that in this case we talk about torque, right? So if we want to calculate torque, we know that that can be calculated by the multiplication of uh, force into moment arm, right? Force into moment arm, and here we can put tangential force. So then for the case of tangential force, we know that we can put R into M into AT, right? So AT is equal to R into alpha. Alpha is the angular acceleration. So if we put the value from here, 80, if we put the value here, then we can write R into M R alpha, right? So Rm instead of 80 we have put R into alpha, and from here we can write M into R square alpha, right? Now this torque is for a single point on that body. So if we want to get the torque which is acting on the entire rigid body, it means that we need to integrate this because we can put differential torque here for that point. So that point on which we are talking about, that is differential torque on that point. So if we want to extend this to the whole entire body, then it means that we need to do integration bit. So for that we can just do the integration, and then that torque in book, this is basically torque. We call it movement and also torque. So that would be equal to R square alpha delta M, right? So we are talking about the whole mass. We are going to integrate it. So because alpha would be the same, so because for the rigid body motion, alpha would be the same. Because the whole body would have the same angular velocity as well as the same angular acceleration. So alpha would come out of integration and R square into dm for the mass. And what is this? We know that this quantity from our statics or dynamics knowledge, that is moment of inertia, right? So we can say that m is equal to I into alpha. Moment of inertia into angular acceleration, that is equal to r, right? So this is the counterpart of Newton law of motion, F is equal to ma, right? So here F is replaced with this moment or torque, and linear acceleration, it is being replaced with alpha, and then mass is being replaced with moment of inertia. Right. So I hope that these two relations are not new to you. Right. So this was about all about the torque. Now we are going to discuss that how to calculate the angular momentum of an object which is moving in, which is in rotation basically. So let me just copy the figure so that uh, we can find out. Just a minute. Okay, before we discuss the angular momentum, what is the linear momentum of a body? We all know that linear momentum of a body is, that is mass into velocity. It is linear velocity. That is, and the direction of the linear momentum would be the same as the direction of velocity. But for the rotation, it is a little bit different, because in that case we are talking about the movement of a force. Because when a body is in rotation, then there is axis of rotation. So the distance from the axis of rotation is very important in that case. So it means that we need to count for that distance as well. So that is called movement arm. So in that case, let me show you the diagram for the sake of clarity. Okay. So now we can see a point which is moving with velocity, tangential velocity v is equal to r omega, and it has got a movement of that angular, that tangential velocity into that what we call it, the moment arm. So the if we take the uh, movement of, let me write it here. Sorry. movement of tangential momentum which would cause some kind of torque that would be equal to that m into v, that tangential momentum into that distance between the perpendicular distance between the axis of rotation and that point. So now we also know that v is equal to r omega, so we can just put the value here. So m into, instead of v we are putting r omega and then r, and then from here we can see that r squared omega into m, right? So now this is also being called angular momentum. Momentum, and this momentum is called angular momentum in this case, and in the book they have shown it by a symbol h, right? So if then again, if we are talking about a point and then we want to calculate the angular momentum of the entire rigid body, so it means that then we need to integrate it from let me write delta h would be equal to r squared omega into delta m over entire mass of the rigid body. So then again, we know that because omega will be constant if the body is having rigid body rotation. So in this case, we can say that omega is outside the integration, and inside we have got r square into del m, which is integrated on entire mass. And again, we can see that here we have got r square delta m, which we know from our knowledge of statics and dynamics that it is moment of inertia. So we can write when we take integral here, so h is equal to I into omega, right? So omega is also a vector form in the interface. We can write it. So angular momentum is product of inertia, moment of inertia into omega, and then the second thing was tau is the product of I into alpha. Here this is m is torque basically. Right. So I hope that these are quite understandable from the prior knowledge. So I just wanted to make sure that you understand these things. So now we are going uh, to to kind of correlate the torque or movement with the angular momentum. So we know that torque can be written as m is m can be written like m can be written like I into alpha. I is again this relation we derived above, and then alpha we know from our knowledge that that is rate of change of angular velocity. So we can write it I into d omega upon dt. Right. So now we have got two properties here, I and omega. Right. So now I would do a little bit of mathematical manipulation here, because we know that h, which is angular momentum, that is I omega, right? So if I take the differential with time on both sides, I can write d by dt h would be equal to d into d by dt I into omega, right? So this is because this is a product of differentiation of a product. It can be written like I into d omega by dt plus omega into di by dt. Because if we are talking about rigid body, which is whose mass is not changing in time, so it means that this second term would be equal to zero, because di or dt would be equal to zero in that case. So then we can write dh by dt is equal to I into d omega by dt. So if we put this here, so we can say that m is equal to dh by, because we can say that these two things are equal. Right hand side, so the left hand side would be equal. So m would be equal to dh by dt. So what does it tell us? That rate of change of angular momentum is equal to net torque of that body. Right? So we know that rate of change of angular momentum is net torque. Right? It is just the counterpart of the linear one, in which the rate of change of linear momentum was equal to net force on the acting on the body. So that is the same thing, and it is kind of counterpart of that. So now, because we usually say that we talk about in terms of RPM. If you remember that we say that the angular velocity, if we want to show angular velocity, so we kind of say that that is in RPM, revolution per minute, and then in one revolution we know that if we talk about in radians, so it covers 2 pi radians. So angular velocity usually it is given by m dot, which is RPM. So when we want to calculate that that angular velocity in radian per second, which is mega, that would be equal to 2 pi n dot for 60. So because n dot is revolution per minute, so in radian it would be we need to multiply it with 2 pi, and then because it is in minutes, so we can make it in radian per second by dividing it with 60, right? So let me, and then if we want to tell that what is the shaft power of a component rotating shaft, then that would be equal to w dot shaft would be equal to, it would be product of torque into angular velocity, right? And then because if we talk about mega in radian per second, it would be equal to 2 pi n dot divided by 60. And if the mega is in revolution per minute, then there wouldn't be any 60 here. It would be only this. So let me show you that the schematic of that, and just a minute. So this is kind of a rotating fan which is moving with the angular velocity mega 2 pi n dot. Now here you can see that mega is in radian per minute, so that's why they have put n dot without 60. So if we talk, so it means that this shaft power would be in joule per minute, not in joule per second. So if you want to have that in watts or joule per second, then we need to divide it with 60 here, as I did in the relation above, right? So that is some, and then that was about the shaft power. Now, if we want to know the rotational kinetic energy for this shaft, first of all, kinetic energy for a system in a linear motion, that is equal to half into, if you remember, that is half into half mv square, mass into velocity square. And now, if we talk about rotational kinetic energy, that would be half into m vt square. So that would be v would be equal to r mega, so r square mega square. And then again, if it is the rotational kinetic energy of a point, and we want to get the kinetic energy for the whole system, we need to do the integration for delta m. So then it would be equal to I, which is again the moment of inertia into I omega square. Okay, we call it K R. R represents rotation. And then when we talk about centripetal acceleration, which is caused by the change in direction of the direction of the uh, direction of the motion due to rotation, that would be equal to AR would be equal to V squared upon R, which is R omega. So I hope that these relations are kind of familiar to you from your prior knowledge. If you acquired maybe during SSC or maybe in the first three semesters here. So if there is any confusion, you can ask me anytime. So that is no problem. So now in many engineering applications, there is a rotational effect like turbomachinery. So in this, we usually have to take the moment of the linear momentum of the flow stream, and then we need to also cater for the rotational effects which are caused by the that movement of the linear motion. So how to calculate the movement of a linear momentum? That is quite simple. And let me show you the diagram first, and then I would explain it from there. Just a minute. Let's suppose that we are talking about a body in which the force is acting in the tangential direction, right? And the perpendicular distance which is in between that force and the axis of rotation, that is r, and that force makes an angle theta with that perpendicular distance. Then if we want to calculate the torque, on that we know that that torque which is represented with m here, that is equal to r, which is the moment arm, into force. So that is the vector product or cross product of that. So when we talk about the magnitude, then because this is a cross product, so we can say that m is equal to fr sine theta. So sine theta is the that minimal distance between the force and that perpendicular distance between the force and the axis of rotation. So please keep in mind this m here is movement of momentum equation, or we also call it torque in our terms. So r is the position vector from point O to any point on the line of section of f, and that f is the force here, and it makes angle theta with that position vector, right? So torque is always the vector product of that position vector and the force vector, and we can write m is equal to fr sine theta. Now, one thing which we need to see, that what is the direction of torque. How can we see that what is the direction of torque? For that, there is a rule, we call it right hand rule, I think. I think that is kind of the thing which we discussed, I think, in SSC as well, if I remember right hand right rule. So that says that if the fingers of the right hand, they are turned in the direction of rotation, then then the thumb points toward the direction of movement vector. So let me show you the figure just for the clarity. So I hope that you're coming across this right hand rule. So it is kind of give you the sense of movement, that in which direction we are talking, because here it is kind of anti-clockwise. So when we have got anti-clockwise motion, then we say that that movement is in the torque is in the positive direction. But if it is in the clockwise direction, then the thumb would always point towards the downward direction. So here you can see that this angular velocity, which is anti-clockwise, shown in the anti-clockwise direction, that produces positive torque. So I hope that this point is clear to you. So you are welcome to ask any question at any point which is not clear to you. So just mind it that we are kind of just revising the basic concepts which are going to be used for the derivation of moment of momentum equation. Because for the linear momentum equation, we derived that in chapter number 5 by using the Reynolds transport theorem, and then for the angular rotation effects, we need to derive the moment of momentum equation. So that is going to be done maybe in maybe 10 to 15 minutes from now. So now if we want to know the give the moment of momentum, which is also called which is uh, moment of momentum, moment of momentum, and we also call it angular momentum, and it is represented with symbol h. That is equal to h is equal to r, which is the moment arm, into m3. Right? Now, this R into V represents the angular momentum per unit mass, because if we divide the whole equation with mass, then cross product with V, that would denote the angular momentum per unit mass, and the angular momentum of a differential mass. If we talk about differential mass now, which is of we can say that dH, differential mass, that would be equal to R cross V into rho into dV. dV is the differential control volume. The volume of the differential control volume. This V is volume here, and this V, which is the vector, that is the velocity vector here. So please don't confuse it with this. And if we want to calculate the total one, then again we need to take the integral of the whole system, and then we can say that h of system would be equal to h of system would be equal to r for e rho dv. And if we want to know the rate of change of angular momentum, then we would divide the both sides with dt, d by dt, r cross v rho into dv. Right? So now we know that the rate of change of angular momentum for a system is equal to net torque applied on the system. So we can replace this left hand side with m. M here they are denoted torque with m, that would be equal to d, that would be equal to dh by dt, and that would be equal to d by dt r cross v go into d. Right. Now once we have seen this, that we can equate the rate of change of angular momentum is equal to the net arc of the system. Now we can write the uh, the correlation between the system approach and the control volume approach by using Reynolds transport theorem. So let me write here Reynolds, the general form of the Reynolds transport theorem. So now we are going to discuss. Right. So if you remember the general form, that is dV system. I had written it in the beginning of the class, so I am going to write it again. D by dt, integration on the control volume rho b dV plus integration upon the control surface, which is inlet and outlet. We are talking about BR, or BR is the relative velocity between the control surface the and the and that fluid. But if the control volume is stationary, then that would be equal to B. So in case of non-moving control volume, right? So if we take B as angular momentum, which is h in this case, so then the small b would be equal to r cross b, because if we remember that h was equal to r cross mb, right? So the intensive property of angular momentum would be r cross b, right? So it means that now if we replace these two things, just let me original equation as well. So we have to replace these two bits, b and I. So if we write dh by dt would be equal to d by dt rho into r cos b dv plus rho surface rho into r cos b b dot b dot m dA. Right? So this is the equation, and then one thing which we can replace here, that we can say that dh upon dt, that is equal to net torque on the system, net applied torque. That is the net applied torque. So if we want to write this in physical terms, that what does each term represents, we can say that the left hand side, it represents the sum of all external movements acting on control volume, because we are talking about the incidence when the system is coincident with the control volume. So we can say that this is movement applied on that control volume, right? And the right hand side we have got two terms. The first term is the time rate change of the angular momentum of contents of CD of the control volume we are talking about. And then the second term here is the net flow of angular momentum out of the control volume. Yeah, control volume. Now, this thing for the steady flow, it would be equal to zero. It would be equal to zero. Now, what is this? The net flow rate of angular momentum out of the CD. It means that if the angular momentum going out of the control volume is greater than the angular momentum of the fluid which is coming in, then this term would be positive, right? So when is that positive? In which case? In turbines or pumps? Because in pumps we usually give angular momentum to the fluid so that it would have more kind of pressure, to build the pressure. So in the pump case, this thing would be positive. But when we talk about the turbine case, when we are getting the energy from the fluid which is coming on the turbine, then this quantity would be negative. So for the pump case, it would be positive. For the turbine case, it would be negative. Because in case of turbine, we take angular momentum from the fluid by the striking of fluid on the turbine blade, so that the angular momentum of the fluid which is leaving, that is less than the angular momentum which came in. So basically, the energy has been imparted on the turbine blades. But in case of pump, because we drive the pump by the electricity, so it means that we are giving that fluid more angular momentum. Right? So this is the basic difference between pump, because in pump we provide work and in turbine we take work from the incoming stream, right? So I hope that this point is clear. So now the rest of the things, maybe because I have shown you the basic things here. So let me take you through the lecture slides as well. So let me share that with you. So board we have covered after this slide, where I have told you about the derivation of moment of momentum equation or angular momentum equation. In case of rotation, we need to solve angular momentum equation instead of linear momentum equation. And as we know that rate of change of angular momentum of a system is equal to net r. So that is m here. So the this physical understanding of this I have told you, and then I have also told you that this first term on the right hand side, that would be equal to 0 if we are talking about the steady flow, and the second term would be positive if we have got a flow through pump, and negative if we have got the flow through turbine. Right. So, and then I also told you that VR is the relative velocity between the fluid velocity. It is the relative velocity between the control surface and the fluid velocity. So here V is the fluid velocity, and VCS, that is the control surface velocity when we talk about moving control volume, or we are talking about deforming control volume, which is the concept of which you must have learned maybe in chapter number 5. So just to give you an idea that if balloon is being expanded, so in that case the control surface is expanding, right? And if that balloon is also being left in the air, then it would also travel. So in that case, there would be control volume would also be moving and also kind of deforming as well. So then, as during steady flow, the amount of angular momentum within the control volume remains constant. So the first term on the right hand side becomes equal to 0, and only the second term remains, which is this control surface term, so which is shown here. And now, in many practical applications, the fluid crosses the boundary of the control volume at certain number of inlets and outlets. So it is wise to write it in terms of inlet and outlet, because we know that the dot product of V dot N would be positive when it is outflow. So the outflow would be always be positive, and then V dot N would be negative for the inflow. So we can write it in terms of like this, that M of dot into R M V. V dot N would be positive, so that outflow term is with the positive sign here, and V dot N would usually have a negative value. So here they have shown it with a negative sign. So because we are talking about net flow out of that control volume, so that's why it is written like this as well. So this first term, that is the unsteady term, which is the rate of change of angular momentum within that content of that control volume, which would be equal to 0 in case of steady flow, and the change in net arc on the system would be represented by these two terms, right? And in case of pump, it would be positive. These, if we take the summation of this, if we get the resultant of these two terms, and in case of turbine, it would be negative, right? So I hope that this point is clear to you. So when there are no external torque applied, then the angular momentum is equal to this, yes, and the contents of that control volume would have higher angular momentum when we have got the momentum out is less than momentum in. So momentum out would be less than momentum in. When it would be the case? When we have got turbine work, because in this case, because the left hand side is equal to 0, then we need to move these two terms on the left hand side. So we can say that angular momentum which is coming into that control volume and angular momentum which is going out, that is positive. It means if that is the case, it means that body has gained the momentum, right? So that is the case of turbine, right? When that blades got speed up due to that the flow which is striking on the blades, right? So if we want to talk about the physical significance or explanation of this equation, that is that in the absence of external movements, the rate of change of angular momentum of a control volume is equal to the difference between the incoming and outgoing. Why incoming and outgoing? Because on the when we take these two terms on the left hand side, it would be in minus out. So that's why they have written like this. When the moment of inertia of the control volume remains constant, the first term on the right hand side of the above equation becomes simply moment of inertia times angular acceleration, which is I alpha, because torque is usually I alpha. So torque is equal to moment of inertia of that body into alpha, which is angular acceleration. So because I have already explained that when we take this term on the other side, it becomes R into mv in minus RMB out, right? So we can use this approach to determine the angular acceleration of space vehicle and aircraft when a rocket is fired in a direction different than the direction of motion. In that case, because these two quantities would be different, because this cross product would be different. In that case, because the direction is same, so we can determine the angular acceleration for those vehicles by the change in direction. Right. So I hope that this is making sense, because this is just the introductory part. We have to apply this knowledge to actual turbomachinery, which is chapter number, I think, chapter number 11 in your book. So this is at the moment this is from chapter number 6 of Angel and Timbala. Right. So many rotary devices such as centrifugal pumps. So, okay, centrifugal pumps, we usually install them in our home when we want to move some fluid from the ground level tank to the upper tank. So, we use centrifugal pumps. So, in this, the flow is in predominantly in the radial direction, which is normal to the axis of rotation. So we call it radial devices. So if I show you the figure, you would recognize these kind of pumps very easily, because these kind of pumps will be very used. So in this case, what happens that the fluid comes from the into the board. It is coming out of the board, and then when it comes out of the board, it travels in the radial direction. So this is eye of the impeller. We call it eye of the impeller, from where the bottom is coming. So this is the frontal view. From the side view, if we see that the flow is coming from here, right, which is we call it eye of the impeller, and then it moves in the radial direction. So we have got some kind of centrifugal force there. So in a centrifugal, so if we read this in a centrifugal form, for example, the fluid enters the device in the exit direction through the eye of the impeller, which is this. It is shown here, right? And then it turns outward as it flows through the passage between the blades of the impeller, collects in the scroll, this big casing that is called scroll, right? And it is discharged in the tangential direction. So it is being discharged in the tangential direction when we look at in terms of this blade. So this motion is in tangential direction going out of this. So we usually see these kind of centrifugal pumps installed in our home. So, and there is a motor as well, which is installed in front of that pump, which is used to produce this motion of this impeller. Right. So we usually call that if we are at home, we usually see this. Okay, we need to switch on the motor. So when we say that we need to switch on the motor, that motor is basically driving that pump, which is installed in front of it. Right. So radial flow devices involve large changes in angular momentum of the fluid and are best analyzed with the help of angular momentum equation which we have derived here. It has got, if I show you the general form that is written here. And let's talk on the control volume, that is the summation of rate of change of angular momentum within the content of the control volume plus the net flow rate out of that angular momentum which is going on out of that through the control surface area. Now let's see that how we can apply it to the this radial form. Right. So here you can see this shroud where we have got B. B is the gap which is available for the fluid to travel. If you see that here the gap is very less, but as we move along this, that gap, this, if here it is B1, here this gap is very significantly higher than this gap. Right. So what does it do? If the gap is increasing, it means that the velocity is decreasing and the pressure is increasing. So because in our home, because we need to have higher pressure so that it can give the gravity from the ground level tank to the upper storage tank. So we kind of it is a diffuser arrangement. You can see that in diffuser the velocity decreases due to increase in cross sectional area, and due to that, if the velocity is decreasing, you know that the pressure increases. The static pressure that always increases, and we need higher pressure so that it can travel against the gravity towards the overhead tank. Right. So it is just to give you an idea. We would do these things in detail. So just to analyze this centrifugal pump, what we do that we take one at the inlet to the, that if we see here, that is the inlet to that impeller, and this is outlet of that impeller. So by the continuity, whatever flow rate which is coming in, that is going to be in the same mass flow rate which is to be at the end of these rotor blades. So one is the outward velocity which is V1N, and tangential velocity which is V1T, and if we see that the resultant velocity would be V1, and similarly here we can see that we have got tangential velocity and the normal velocity, and the resultant of that velocity which is the actual flow direction, that is this. Now when we talk about the mass flow rate, we are concerned about this normal component which is going out, right? And when we talk about the generation of torque, then we are more concerned about this tangential component. This because this tangential component is going to create torque, and this normal component that is going to determine the mass flow rate through that pump. So the average velocity in general has normal and tangential components at both the inlet and the outlet of the impeller section. So inlet of the impeller section, again I would say that this is the inlet of the impeller section, and this is the outlet of the impeller section, where the blade section goes ends. So the velocity which is coming here, it has got two components, tangential component and normal component. And similarly, the velocity would have two components on this outer tip, right? So the average flow velocity has this. So I have told you. So when the shaft rotates at angular velocity omega, the impeller blades have tangential velocity omega r1 and omega r2, which is the blade velocity. U is equal to r omega, right? So that is the tangential blade velocity, right? So here, because at the this because the tangential component would be less, because that r radius is less, because omega is the same at both locations. So r omega, when it would be more, the tangential velocity would be more at the outlet of impeller blades. So for studying compressible flow, the conservation of mass, we can say that here you can see that we have equated the volume flow rate here, and we have used normal component which is going out, V1N and V2N, because that is the component which would determine the mass flow rate or volume flow rate, that normal velocity component which is perpendicularly outward from this axis of rotation. So B1 and B2, as I have explained here, that B1 is the gap which is shown here, which is less, but as we move away, we can see that this gap increases. So that's why we would have B1 would be would be less than V2, right? And then V1n would be equal to V dot upon 2 pi R1 V1 and V2n, and then we can, if we know the volume flow rate as numerical parameters R1 and V1, we can calculate V1n and V2n, which are responsible for the mass flow rate through that pump. And then the normal velocity components as well as pressure acting on the inner and outer circumferential area passes through the shaft. Now, one thing, that tangential component only is responsible for the torque or movement. The normal velocity component, because they are passing through the axis of rotation, there is no movement arm for this V2n and V1n, because they are passing through that axis of rotation. So R value is 0 for that. So they are not going to produce any contribution in the torque. The only contribution that would be coming from this tangential component, which is at a R1 distance, and V2t, which is at R2 distance, right? V2n, it is passing through the center, and V1n, that is also passing through center. So they are only responsible for the mass flow rate through that pipe. They are not responsible for the torque contribution. So we can say that if we have got the steady flow, then in this equation, for the steady flow, the first equation would be, first term on the right hand side would be 0 for the steady equation, and this net torque would depend that what is the force on that net torque applied by the generator, and then here these second two terms we would have these second two terms. Yes, anything? Any query? Somebody unmuted his mic. If you want to ask anything, you can ask now. Okay, maybe it was by accident, so we can just keep on going here for 2 minutes, and then we would have a break for a quiz. So these are the two terms which are going to remain on the right hand side, this second term and third term. So in that, if we see that that is equal to m dot into R2 V2t. V2t is the angular momentum which is going out, minus m dot into R1 V1t, which is the angular momentum which is coming in. So that is called either turbine equation or turbo equation, not maybe not turbine equation, because we are talking about form, but we call it Euler's turbo machinery equation. We can call that. If we want to calculate the resultant torque, then that would be equal to this difference in angular momentum at the outlet minus angular momentum at the inlet. So we just keep it here, and then we will start it from here in the next class, which is in fact tomorrow, next class. So please understand that this turbo machinery is the major application area of fluid mechanics. So in industry, it doesn't matter if you go into industry or military, everywhere there are some kind of rotating parts inside engines. So you need to know how these principles work when we talk about the fluid mechanics principle, how they are applied to rotating parts which are basically turbo machinery. So this is the major application area, and we are going to discuss it in detail as much as we can in